Okay, so this is the beginning of our new topic on logarithms, and logarithms are very closely connected to indices, exponential functions, etc. So before we get started on introducing the idea of a logarithm, what it is, how we work with them, we just need to take this lesson to review our understanding of indices and index laws and also of exponential equations, all of which we looked at back in semester 1. If I remember, I'll link to some of the relevant videos from semester 1 here at this point. But yeah, going back to the topic on indices, certain indices would include a lot of this. Okay, so let's just recall our index laws. By now it's assumed that you know and can use these laws. Okay, so going into Year 11 Math Methods next year, we'll absolutely assume that you know how to work with indices, both positive, negative, and fractional. And so if this is something that you are not very good at, perhaps going back to some of those videos from the semester 1 topic and looking at this in a bit more detail. Okay, so let's just recall those index laws. So when we are multiplying two indices with the same base, or two powers with the same base, we can simply add the exponents. Okay, so that is a, so exponent being, the power. Technically speaking, the whole thing is a power. The a is the base and m is the index or the exponent. Okay, so if we add the exponents, we get a to the power of m plus n. And again, this only works if it's the same base. So if it was, 2 to the power of 2 times 3 to the power of 2, it doesn't become 6 to the power of 2. Okay. Well, actually, in this case, it does because they're both powers of 2. But we don't add. So the point is that we don't just we can't just multiply the bases. Okay, so a to the power of m divided by a to the power of n. So when we're dividing two powers with the same base, we can subtract the exponents. So this would be a to the power of m minus n. When we have one power after another, so a to the power of m and then that to the power of n, we can multiply those exponents. So a to the power of m times n. If we are multiplying two things, all to the power of n, we can simply apply the power to each of those two things, a to the n times b to the n, Similarly, if we're dividing, a over b all to the power of n is the same as a to the power of n divided by b to the power of n. A to the power of 0, anything to the power of 0 is always 1. Okay, then we've got our negative exponents, so a to the power of negative 1 actually means that we take the reciprocal of the base, so we get 1 over a, so it's 1 over a to the power of positive 1, so it's just 1 over a. If the negative power is already on the denominator, then it moves to the numerator. So essentially the negative power we can think of as sort of telling you I'm on the wrong side of the fraction. So if you've got a negative power on the numerator of a fraction, which is what we have here, it needs to go to the denominator with a positive power. If we have a negative power on the denominator of a fraction, it needs to go to the numerator, but with a positive power. So it becomes a to the power of positive 1 over 1, so it's just a. So generalising that a bit further then, a to the negative n is 1 over a to the n. 1 divided by a to the negative n, the a to the n goes to the top, so that is a to the n. A fraction to the power of negative n, we can take the reciprocal of that base, so that is b over a to the power of positive n. You could think about that in a much more long-winded fashion. You could think about that as using this rule first to expand that out, so that's a to the negative n over b to the negative n, which means that both those things are on the wrong side of the fraction, so a to the positive n on the denominator and b to the positive n on the numerator, and then we can reverse this rule over here by saying, well, that's the same as b over a to the power of positive n. So all those are the same thing. So essentially, though, it's all about taking the reciprocal of the base, the negative power. Fractional powers are to do with roots, so a to the power of a half is the square root of a to the power of a third is the cube root of a, not 3 times the square root, just be careful how you write that. A to the power of 1 on n is the nth root of a, again, not n times the square root, so the nth root of a. And so making sure that the n really sits in the crook of that square root. Okay, so perhaps if we do the same here, a bigger crook so we can fit the 3 in here. Square root, yes, you can write square roots as square root of a, but that's the most common root, so when we omit the 2, we understand it to mean the square root. And then if we've got a to the power of m over n, we can think about that as sort of being two things happening at once. So we can think about that as being, think about that as being a to the power of 1 on n times m. We know when we're multiplying powers, that's because we're applying one power after another. So that's the same as having a to the power of 1 on n, then to the power of m. So that's the nth root of a to the power of m. Okay. You can also think about it in reverse. You could think about it as a to the power of m times 1 over n. So that's a to the m to the power of 1 on n. So it's the nth root of a to the m. But usually in practice, if you're trying to evaluate something to a fractional power, a non-unit fraction, it's easier to take the root and then raise it to a larger power rather than do that in reverse, because it's easier to make the number smaller before you then make it bigger again. It should be recalled that the following expressions cannot be simplified or expanded using index laws. So a plus b all to the power of n is not a to the n plus b to the n. As much as you all want to tell me that x plus 3 all squared is x squared plus 9, it isn't. You cannot just expand out in that way if it's a plus. That's x plus 3 times x plus 3, which is x squared plus 6x plus 9. It doesn't rely on the index laws. Similarly, if you have subtraction, it's not a to the n minus b to the n. You have to be able to expand it out. We also can't put these together. There's no index law for when you are adding powers with the same base, nor for when you are subtracting powers with the same base. Okay, so let's just work on simplifying some expressions involving index laws, and then we'll review our exponential equations. So generally speaking, I tend to like to follow a similar pattern. I try not to do too much cancelling out. You lose track of what's happening. Be clear about what's going on. So let's worry about those brackets first. So we're going to have 2 to the power of 4, which is 16, times p squared to the power of 4, which is going to be p to the power of 8, multiplied by 3 to the power of negative 2, I might just write that as 3 to the negative 2 for now, times p squared to the negative 2, so multiplying those powers, 2 times negative 2 is p to the negative 4, and that's q to the 1 to the power of negative 2, so that's just going to be q to the negative 2. Okay, let's think about that 3 to the negative 2, that's 1 on 3 squared, so that's 1/9. Okay, so we've got 16 times 1/9, let's just write that as 16 on 9. We've got p to the 8 times p to the negative 4, so we add those powers. 8 plus negative 4 is positive 4, and we've got just q to the negative 2. Now we want to express the answers with positive indices, so that q to the power of negative 2 needs to be q squared on the denominator. The p to the positive 4 can stay on the numerator. So let's now write this then as 16p to the 4 over 9q to the 2. Sorry, 9 and q are a bit similar. You might also have decided right at the beginning here to write this as, 16p to the 8 over 9, oh well, you could have just gone for this for a minute, 3p squared q over positive 2, and then worried about simplifying. Personally, I tend to kind of worry about the negatives right at the end. You can faff around with the negatives a lot at the beginning and find that if you hadn't worried about it, by the time you got to the end, there weren't any negative powers anyway. So I tend to worry about the positive indices thing later on. Okay, 15c cubed d over 12c to the negative 2d to the negative 3. Let's just focus on, sort of dividing the like terms if you want. 15 on 12, that simplifies to be, it's got 3 as a common factor, so that's 5 on 4. C to the power of 3 divided by c to the negative 2, we subtract powers when we're dividing, so 3 minus negative 2 is 3 plus 2, so that's c to the power of 5. And then d, it's d to the 1 divided by d to the negative 3, so we're subtracting the powers. 1 minus 3 is 1 plus 3, so that's d to the power of 4. So as I said, you can worry about these negative powers at the beginning, but if you just focus on simplifying, look, we don't have any negative powers at the end, so, don't work too hard on the negatives at the beginning. Alright, you can leave it as that, 5 on 4, c to the power of 5, d to the power of 4, we've got positive indices. You might choose to write it as one combined fraction, these are over 1. So it's 5c to the 5, d to the 4, all over 4. They're the same. Okay, one's not more simple than the other. Okay, this one here, let's do a couple of things. So we need to be a bit careful here. We've got both the divided and the negative. So before I worry about the division, I think what I might do is worry about this power here first. So maybe let's expand out the brackets first. So we're going to square everything in this first bracket. So a squared squared is a to the power of 4, b cubed and then squared is b to the power of 6, over b to the negative 2, that's b to the negative 4. So yes, okay, there's a negative power in the denominator, we could worry about that. Let's worry about that later, let's just do one thing at a time. So the first thing I'm doing is expanding the brackets. We're dividing. Let's expand out these second brackets, so that's going to be a to the negative 2. Well, in fact, rather than expand them out, I might take the reciprocal first to the power of positive 2. Okay, so it's going to be a to the 4, b to the 6 over b to the negative 4, divided by, that's going to be a to the power of 4 over a squared b to the power of 8. Now let's worry about the division. So we've got a to the power of 4, in fact, sorry, I probably should have done this simplification at this point. So perhaps let's, it's up to you. I'm going to leave it actually. Sorry. Okay. So a to the 4, b to the 6, well, let's do it here. A to the 4, so we've got b to the 6 divided by b to the negative 4. So 6 minus 4, so that's actually b to the 10. And we are going to multiply that by, I'll simplify this fraction after I've flipped it, a squared on b to the 8 over a to the 4. So maybe let's now put these together. So we're going to have a to the power of, we add those powers, a to the 4 times a squared is a to the 6, b to the power of 10 plus 8, which is b to the 18, over a to the 4, and then we can simplify our a to the 6 over a to the 4, so subtracting those powers, a squared b to the 18. Again, we could have, simplified these a's earlier on if we wanted. Oh, sorry. Yeah, so there's lots of different orders that you can do things in, but just try to be a bit systematic. I tend to worry about brackets first, then doing divisions and multiplications, then simplifying within the fractions, and then at the end worrying about if I have any negative powers, expressing with positive powers. Okay, again, D, let's expand out all those brackets would be my first priority. So this is 3x to the 4, y to the negative 8, so multiplying those powers, over, this is 2x squared y to the 4. I might change this to multiplication and flip at the same time. So we're going to have 3 squared, which is 9, x to the negative 4, y to the 8, over x to the negative 3, y to the negative 3. Now, again, we could worry about simplifying these separate fractions. Personally, I always get the multiply together first and then do the divisions. Okay. Again, it's just about having a process so that you don't accidentally skip steps or you don't sort of jumble things up. So I'm going to multiply the two fractions. So 3 times 9 is 27. X to the 4 times x to the negative 4. Well, that's actually just x to the 0. Might just write that for the purpose of being able to simplify the division in a bit. Y to the negative 8 times y to the 8. That's also y to the 0. Actually, I'm not going to write it. So we've just got 27 on the numerator. On the denominator, it's 2 times 1, so it's just 2. X squared times x to the negative 3, so that's x to the, adding them, 2 plus negative 3 is negative 1. And y to the 4 times y to the negative 3, we add 4 and negative 3 to get positive 1. Okay, so we've got a negative power here, so it needs to actually be on the numerator. So what we actually have here is 27x over 2y. 27 on 2 doesn't simplify, everything else is simplified. Okay, so just an understanding of your index laws. The next thing we want to just recap before we move on to introducing the logarithms in our next video is exponential equations. So when attempting to solve an exponential equation, our first aim is to try to express both sides of the equation as a single exponent with the same base. And then we can use what we call the one-to-one property of exponentials, and that is that if a to the power of x is equal to a to the power of y, the only way that that's true is if x equals y. So once we get our equation as a to the power of something equals a to the power of something, we can then equate those two exponents and lose our exponentials altogether. Okay, so the first aim is to get to that point. Same base on both sides, single term with the same base. Okay, so in this instance, we've got 3 to the power of x plus 3 equals 81. Now 81 is also a power of 3, so this is 3 to the power of x plus 3. 81 is 3 to the power of 4, and so now that both sides are a single exponent with a base of 3, we can now say equate the exponents and say that x plus 3 is equal to 4, and so therefore x is equal to 1. Okay, part B, 10 to the power of x minus 5 equals 1 on 1,000. Okay, so this is 10 to the power of x minus 5 equals 1 on 10 cubed. So that means 10 to the power of x minus 5 equals 10 to the power of negative 3. We've got both sides with the same base. We can now equate the powers. X minus 5 equals negative 3. Adding 5 to both sides, x equals 2. Okay, part C. We want to try and write both sides with the same base. Now, the left-hand side has a base of 2/5. Now, this is 5 squared and 2 squared, so we should be able to get there as well. So this is 2/5 to the power of 3x minus 5. Now, this is 5 on 2 to the power of 2. So if I want to take the reciprocal, this is going to be 2/5 to the power of negative 2. Now I have the same base, so I can say that 3x minus 5 is equal to negative 2. We can add 5, so 3x equals 3, and therefore x equals 1. Okay, part D. Now 32 is not a power of 8, but both 8 and 32 are powers of 2. So let's focus on writing everything with a base of 2. So 8 is 2 cubed, and we've got that to the power of 5x. And 32 is 2 to the power of 5, and we've got that to the power of 3 minus x. Okay, our index laws then tell us that we multiply powers when we're in this situation. Oops. So we're going to get 2 to the power of 15x equals 2 to the power of 15 minus 5x. Now we have a single exponent with the same base on both sides of the equation, so we can equate the exponents. 15x equals 15 minus 5x, adding 5x, 20x equals 15, and so x is 15 on 20, common factor of 5, so that is 3 on 4. Okay, and then part E. Again, we still want to focus on writing both sides of the equation as a single exponent with the same base. Okay, a single power with the same base. So here I've got bases of 5, 25, and 125, so I should be able to write them all as powers of 5. So we have 5 to the power of 3n already. 25 is 5 squared to the power of 1 minus 2n. 1 on 125 is 5 to the negative 3, because 5 cubed is 125, so 5 to the negative 3 is 1 on 125. Okay, let's just multiply those powers together. And then we also want to think about combining this together because we need a single power on each side of the equation before we can equate the powers. So this is 5 to the power of 3x times this is 5 to the power of 2 times 1 minus 2n, so 2 minus 4n equals 5 to the negative 3. Okay, then we're now multiplying with the same base, so we can add the powers. So we have 5 to the power of, sorry, it shouldn't be 3x, should it? It should be 3n. My apologies. 5 to the power of 3n plus 2 minus 4n, so adding the powers. Let's just tidy up that power on the left-hand side, so that is 2 minus n equals 5 to the power of negative 3. Now we have a single power on both sides, we can equate the power, and they've got the same base, we can equate the exponents, so 2 minus n is equal to negative 3. Taking away 2 from both sides, n equals negative 5, and so therefore n is equal to 5. Okay, last equation. We want to focus on trying to write everything here with a base of 6, because 36 is 6 squared. Okay, so let's do that. So the numerator is 6 squared to the power of 3 plus 2n over, we've got 6 to the power of n equals 1. Now, what we could do is we could just multiply both sides by 6 to the power of n. Okay. The other thing you could do is, I'm going to show you this just because I think it'll come up, it'll be a bigger issue in other equations. We could think about how do we write 1 with a power of 6? Well, it's 6 to the power of 0. Okay. So then we can multiply the powers on the numerator here. So that's 6 to the power of 6 plus 4n over 6 to the n equals 6 to the 0. Then we can subtract powers because we're dividing with the same base. So we've got 6 plus 4n minus n. So that's going to be 6 plus 3n equals 6 to the 0. And now 6 plus 3n equals 0. 3n is negative 6, and so n is negative 2. As I said, a few different ways you can do that rearrangement, but being able to be flexible about how you use your index laws to focus on getting both sides as a single exponent with the same base. Now, there'll be lots and lots of equations where it's impossible to write both sides with a power with the same base. So, for example, if I have 2 to the power of x equals 4, 4 to the power of 2, so that's fine. Again, if it's 16 16 is a power of 2. If it's 8, 8 is a power of 2. Okay? But there are plenty of numbers, infinitely many numbers that are not powers of 2. If this was 2 to the x equals 3, or 2 to the x equals 7, or 2 to the x equals 51, we would not be able to write both sides with the same base, and so this method wouldn't be helpful. And that's where we're going to need logarithms, and so that's where we're going to move on to over our next couple of videos. So today's work is from a worksheet just reviewing and practicing index laws and exponential equations. In our next video, we'll introduce the idea of a logarithm.